Hello everyone, my name is Rama Gordhanam. Today I'm presenting my peer graded assignment for the course Machine Learning Foundations for Product Managers offered by Duke University's Pratt School of Engineering. In this project, we will build a model to predict electrical energy output of a combined cycle power plant. We have a set of 9,568 hourly average ambient environmental readings from sensors at the power plant, which we will use in our model. The columns in the data consist of hourly average ambient variables, and the project objectives are identify the most effective machine learning approach, select the best combination of features and algorithms, evaluate and compare model performance, choose the model with the best accuracy and efficiency. As part of data preparation, I split the 80% training data and 20% into testing data. This allowed me to train and evaluate multiple models, comparing their performance before selecting the final one. To understand the relationship between variables, I plotted each independent variable against the energy output. Visualizations showed a strong linear correlation. I selected multiple linear regression as the modeling approach. Approach After training a multiple linear regression model on 7,654 observations, the following key insights were observed. The model achieved an R2 0.92, indicating that approximately 93% of the variability in energy output is explained by the selected environmental features. Here are the coefficient values. This high R square suggests a strong linear relationship between the independent variables and the dependent variable. It's confirming that the linear model approach is appropriate for this. Uh, Relative humidity had the smallest coefficient among the variables, indicating low influence on the prediction of the energy output. For this reason, I'm excluding RH for relative humidity for the approach 2. And my model selection, I'm considering all four features or variables for the approach 1, and I'm excluding um, relative humidity RH for the approach 2. In approach 2, I used three variables to train the model for 7,654 observations, and my R2 is 0.9185, almost 92% of variance, and here are the coefficients for the approach 2. And coming to the approach 1 result, to evaluate and validate the model, I used three key metrics: R square, MAE, RMSE, MAPE. These metrics show that the model performs accurately and reliable on the test data. Coming to the test results, these five columns are test data columns, and I calculated values for the rest of these columns. Predicted P absolute error, square of error, absolute error percentage, and the R square, MAE, RMSE, MAPE are here the values for approach 1, and approach 2 results. As I excluded relative humidity, here we have four columns of test data, and I calculated with the coefficients, and I got the values for these rest of columns. And my R square, MAE, RMSE, MAPE are here the values, and both results, if I compare, comparing the both results, approach 1 R square 9.2, approach 2 9.2, and MAE, RMSE, MAPE. So MAE, RMSE, MAPE should be as low as possible, since these metrics indicate the errors. R square should be as high as possible, since it indicates that the model fits the data. So the conclusion is, after comparing above both approach results, we can conclude the approach one, where we included all four independent variables, is a better model to predict electrical energy output. And thanks for watching. Thank you.